Hi everyone, welcome to the Formative Viva presentation. I'm Ashwin Vijay Kumar. I'm presenting about concept drift, face recognition and federated learning. So the project is about a private gallery held by users, which is absolutely not shared among people, and it's hidden with their mobile phones, for example. So the objective is to recognize people, and the DevOps kind of finds it difficult to retrain the models every time because the older people are not detected properly. And that's why I'm here to do face recognition, concept drift, as well as a federated face dataset learning. Then the concept drift is evaluated using F1 score or recall score, F1 score in drift. Um, then the motivation is about we have the stakeholders are data scientists, data analysts, data engineers, project managers who generate visualizations, model development, lead operations, and the project. Then they do face recognition. Then I'm focusing on face recognition as well as concept drift. I'm developing machine learning implementations that will detect concept drift uh, on images, for example. So these are my progress on the current objectives. So I've got objective 10 objectives and objective 1, 2, 4, 5, 6 and 7 have been started. The progress on proposal phase, I keep meetings at the end of every proposal phase, and this is my timeline. The initial project phase, I've reached till the end of drift adaptation. The drift adaptation is implemented along with GAN inference. So drift adaptation has been held now, but I'm chasing upon that. Then this is description of the project phase. I have to set up the FedML and they keep the meeting every 2 weeks. This is final project phase where the project iteration ends. So my objectives are dataset analysis, concept face recognition, statistical analysis of datasets using FaceNet, and statistical analysis of faces using statistical face models. So let's go on to dataset analysis. This is preliminary results and specifications. So in the dataset analysis, I've got three datasets. One is AgeDB, FGNet, and CACD 2000. So AgeDB is exactly same as the Gaussian distribution. We have low amount of images in the 0 age or 1 age, and low amount of images in the 101 age. So age is on x-axis and count is on y-axis. On the FGNet, we have large amount of younger age people, and it reduces until 69. And on CACD, the celebrity dataset, which varies from 14 to 62, similarly looking like a Gaussian. So this is dataset analysis on identity distribution. I've got AgeDB, CACD 2000 and FGNet, 567 identities for AgeDB, 16,488 images, 1 to 101 age range. CACD 2000 identities, 163,446 images, 14 to 62. FGNet with 82 identities, 1002 images, and 0 to 69. Then AgeDB, the mean of age is 46. CACD, the mean of age is 38. FGNet, the mean of age is 15.84, and you can refer to these standard deviations as well. This is directly from the Python code where you apply describe or describe. So these are about comparing groups of people, groups of Euclidean distances arranged over people or identities for AgeDB. And we can see that all of the images are in the same range of Euclidean distance, so it is very difficult to classify them using images, using identities. So you have to either cluster them using group them using Euclidean distances and then classify them later, or you have to directly classify them using embeddings. So this is kernel density of Euclidean distances. The kernel density is arranged according to the age group. I've got for all of the same identities the kernel density, and I can see that the Adolf Hitler one is actually deviating, the age group is deviating from the rest of the other people. Then the concept drift. So this is addressing tabular data using data streams improves automation. Addressing image data using datasets improves pipelines. Evaluating concept drift for tabular data and images differ because of the evaluation methods. The methods have been developed to explain concept drift in a model. Dataset analysis is the key to our understanding, such as the dataset metadata. So let's move on to the next one, which is concept drift on images and data. This is an example sample dataset made with Meek-Moons of scikit-learn. Then I've got a scatter plot on the left hand side and the real drift solved by SVM decision boundary on the right hand side. It gives a 98% accuracy. I've plotted first feature on the x-axis and second feature on the on the y-axis. It's a straight decision boundary, same as a face recognition model, I believe. So this is using clustering. This is virtual drift directly on the data without getting the ground truth. So this is solved using the spectral clustering. So you almost get a good split of data. Then this is concept drift by age. So we have some research questions. This is some of them which I have shown it here. The first is we need to identify whether the model or data drifts by age. We need to identify if the virtual drift is applied or real drift is applied for a particular use case. We need to identify if the drift is severe for virtual and real drift. Then age related concept drift is considered as time variant drift on a particular phase. Need to identify methods to evaluate the model drift and the data drift. A statistical analysis of the concept drift due to model and data is presented in the next slide. So this is statistical analysis of data using FaceNet. The FaceNet model I downloaded is the KRS one with H5 weights. And I've analyzed HDB, CACD 2000 and FGNet. I've got a graph looking like high variation on the ends and low variation on the middle, and almost almost same mean on the middle, which is for HDB. For CACD, it's almost varying for every size. It keeps on varying for some iterations. Then FGNet also is looking similar for most of the images, but there are variations in some. This is done using multiple iterations, like 25 iterations of p-values of the confidence intervals. I calculated mean of Euclidean distances, for which the results table has been provided. Then standard deviation and standard error of mean, as well as the count. And then I calculated the t-values and p-values as well. So this is a scatter plot of HDB against age for Euclidean distances. Then we can see that it somewhat climbs, the average line climbs from 0 to 100, which is a direct inference indicating there is a drift by age. So the scatter plot is actually mean of Euclidean distance over age. So there are this is a comparison table x by m by n, and you take average over one axis and then plot the Euclidean distances over age. Then this is a results table I want to show. So here we have ages from 1 to 101, and on the ends actually it's drifting, in the sense this is because the number of samples you see, the Gaussian distribution is very low, and maybe the error is high, and it's a mean. It's actually mean values. So mean as well as standard error mean as well as standard deviations. So they show a lot of variations here. And on the middle is almost the same. So this is results mean aggregated over 10 discrete age values by taking rolling sum of them. So when you take sum of them, you see that there is a drift, there is a kind of drift or higher higher mean at the higher ages and lower mean at the lower ages. So this starts from, you can see this starts from 24 until 101 for the ages. Sorry, for the samples, for the number of samples. Then this is standard deviation, which is almost the same. This is standard error. So standard error is actually higher drift at the edges, the higher age when you get older, and little bit of higher from the mean, from the middle ones on the top part. So this is calculated by taking rolling sum. Standard error is higher at the higher edges. So I calculated power statistics because p-value is not maybe a good statistic. It does not got any permutation testing. So I did permutation testing along with the power statistic by taking a 0.99 difference, and I got similar heat map like this one, 12101, 12101 here. The zero values indicate there is no detection, nothing has been, no change has been detected here, and the darker red values, white values indicate there is a detection, which means power is 1. So here is comparing group of images in one age group for false discovery rate and alpha, beta and alpha. So here is another study that indicates that FDR on young and old images are higher than those in the middle. FDR states that probability of real difference given test is significant, measured with 0.99 confidence interval for face recognition using FaceNet. These are tables. The results state that when the face is young and old, the type 2 error is higher than the middle ones. So you can see it's a little bit higher on the edges, 1 to 16, then on 0 in the middle, and on the right extreme edge it's actually a little bit higher. So alpha is a signal as well, which is varying. It's almost same in the middle and higher at the end. So power is an indicator of alpha as well as beta as well as variability as well as mean differences. So power calculation inferences, when ones which detected may explain drift statistically according to confidence interval or p-value and false discovery rate. For the calculation of p-value of a single sample, so if there is only one single sample, like for example age 1, you apply one sample test which corresponds to the power. Then here actually what works well is when power is 0, it's not detected for change. When power is 1, it's detected for change. When power is 0, mean differences are consistently low. When power is 1, mean differences are consistently high. Power is 0, variability may be present in some, because variability is conditional to increase the power and decrease the power. And power 1 means variability is low. Again, that may it may be low. Then power 0, we cannot say about sample size, and power 1 we can say the sample size is large, must be large, then that works well. So the statistical hypothesis on image similarities, the difference detected is significant along with FDR, which is moderately low, as we showed as I showed the FDR table. This also implies that explaining the drift at younger and older ages is irrespective of the image properties. So the drift is there, a little bit of drift is, a little bit of power and beta signal is there, but it's irrespective of the image properties such as orientation, background and lighting. So this effect is also seen in ages of 51 to 54, which is somewhat in the right middle extreme for CACD 2000. Drawback. Another drawback is have not taken into consideration the virtual drift occurring on the data. So the images can have drift, or the change in images such as noising an image can have a drift on the neural network model. So this is a decision model that I formed based on a paper. According to a paper, the drift severity is more for real drifts and less for virtual drifts. So it also states that when the drift severity is high, the knowledge loss is also high. So real drifts show high drift severity. Then this is statistical phase model using PCA on images. Here is a process where you extract the images, then you do PCA on covariates, finding eigenvector coefficients, then finding weights and finding Mahalanobis distances, then grouping the images based on Mahalanobis distances. Then we can either, when we amend the weight type of weights, the shape of weights, you actually get image reconstructed images as well as image perturbed images, which we can use for drift synthesis. And for phase aging, actually we have to apply coordinate transforms and other kind of spatial transforms to do the phase aging. This is a 1992 or 2000 that type of technology we are using, which has been mentioned by this project. But we are using only till the drift synthesis part, where image reconstruction is there, which is applied to do the drift synthesis. Then explaining the drift on images. So drift explained by age. This on the left hand side is image reconstruction and image noising. The first image is the original image. Second image is a PCA image. Then this is denoised original. This is denoised PCA. This is residual original. This is residual PCA. This is another sample almost looking the same, but it's a bit different. Then drift explained by grouping distance. So this is when the weights, the shape of the weights conform to the dimensions, but it solves the purpose of doing the image perturbation, because it changes the classes and we get a good plot. Then the image perturbation, using image perturbation, this is for one particular set of data where the distances are almost similar, and we get a sort of phase structure here. When we apply that phase structure, when we add it to this data, the image still remains the same for the naked eye, but it changes the decision boundary for a neural network or an SVM classifier maybe. Then the another image for different distances, these three. This is the aging function or the noise. Then here the another aging function is crystal clear. Actually, it's similar to the image, but appearing differently. So here is a plot of Euclidean distances of similar and non-similar images. This is captured while I trained the transformers model for creating phase recognition model for HDB and CACD. On the left hand side you can see HDB is there. On the right hand side is the CACD 2000. So this is I plotted non-similar and similar images because we need to do that for the transformers model, and Euclidean distance is plotted on the right hand side on the x-axis, and cosine similarity is plotted on the y-axis. You see that the decision boundary is quite difficult to split over a clustering method, for example using Euclidean distance, and even for the classification method. So this is the method I synthesize using this process, where image perturbation is applied, which I got a drift synthesis plot by Euclidean distance and cosine similarity. The red indicates false negative and blue indicates true positive. And using phase aging GAN, I just calculated a heat map, and the distribution shown. So the distribution is concentrated on the right hand side and left hand side for a single sample image, for one sample image, which is so if you increase multiple samples, obviously there will be there will be a huger distribution and the spaces will be filled. But this is a GAN example. This is a lot of samples actually. This will be, if this is a lot of samples, this will be more populated, and over age variable. So GAN has a problem that GAN we have to do an adaptation over the model, over the image, or we have to change the image to a different age, and we have to compare the distances over that age and plot the values. So for drift synthesis, I was just comparing about the GAN model versus a statistical phase model on the left hand side, and which one works better. The statistical phase model eliminates all the aging properties and shows us results like these. We'll go into that detail. This is face recognition. The face embeddings are post-processed by ensembles of SVM, KNN, and random forest and His gradient boosting which is inspired from LightGBM. Then the accuracy for the face model, actually there is a voting classifier I got is 88.49, and that is including 3 classes per ensemble trainer. A voting classifier takes predictions from various algorithms and combines it to one prediction by soft voting. These are the predictions here. So when I predict, it's obviously 1 for single image, because I take a comparison, and then for Adolf Hitler is 0. For others, it's actually 1. I'm coming to be 1 for the unseen data, test data, which is about 1,000 samples of data. But 3 classes per voting classifier. Then next slide is about explaining machine learning predictions using SHAP. Then this is on the left hand side, we can see 109 feature is split across the SHAP values. The red and blue indicates that it creates a sort of decision boundary which can be separated by a different classifier, and the decision boundary kind of reduces. This is a prediction from one of the identities from HDB. Then checking age drifting using machine learning. So this is, we know that voting classifier is used to classify them. Then using face embeddings but ordered by age, a voting classifier is trained with younger faces and tested on older faces. The experiment revealed a drop in accuracy by 3.88%, which is for the age drifting. And such a drop is explained by change in decision boundary. The real drift occurred in this case is measured by a classifier algorithm. The real drift explained statistically by virtual drift in the image data, and some by concept drift explained by Euclidean distances, which we can refer to. Then this is the voting classifier results. On the left hand side is 88.49 plus this error 0.10017. We can see that the standard deviation is higher on the right hand side. This is because of the age drifting, and the mean accuracy is low. This is weighted accuracy actually, so for number of classes which has been predicted. For some predictions, the classes are 100, 114, 102, 112, etc. And the number of image samples. So the classes are 3 itself, but I've taken number of training examples into consideration for calculating the accuracy score, and taken a weighted average which is normalized into 88.49 and 84.61. Then this is voting classifier for face classification, which is SVM classifier. So on the left hand side we can see there's a huge spike for the close to 0 C values, and on the right hand side as well age drifting, but the distribution has changed a bit. This has reduced and it has come across other values. This slightly indicates there is a change in the balance of parameters over the voting classifiers. I have used the exact same examples for a voting classifier for the samples as well as age. So this is random forest classifier where the shift is kind of looking into, but we cannot see properly. There's complete picture here, this complete picture here, and this one here. But when you get onto this one, this is almost splitted into same. This shows that the age drifting has been happening on the min sample split on the depth of His gradient boost depth of 3 and 5, but here actually on 5 dominates. So here is min samples leaf, almost similar. We can see there is similarity for 5 and 10, so we don't know which one to choose, but it chooses based on the classes. And here 5 is dominating. So here is another example where I actually tried statistical drifts, explain the statistical drift on images or data by age. So what I did was, I've got the samples here, the original image, the PCA image. I compared the original and PCA image plotted as yellow scatter plot, which has been shown on that other slide, and I plotted original image and denoised original. So this is the right hand side is the yellow scatter plot where I actually compared original image and the aging function, which is a PCA image from the statistical PCA model, face aging, and I can see that there is a climb, there is a drastic climb from a big value. The separation is 5 here, the separation is 1 here, from probably 27.5 to 30. And here actually there's a climb from 11.75 to 12 probably. Then I compared original image to the denoising image and aging function to the denoising image and plotted the PSNR. So PSNR is a metric which also evaluates the quality of the image. Explaining the drift on images or data. So PSNR of original image and noise image is equal to amount of noise filter for that age group. So noise filter is a parameter which is mentioned in a couple of papers, and what it does is when you add the noise filter, what it does to clustering is GMMs would unclass a particular class, the decision boundary will change, but some classifiers do not detect the difference. Some classifiers will outperform that, but even if the noise filter is applied, the classifier will outperform that. Anomaly detection would detect better under noise filters as well. Then the effect is that the CDA fed average method, which is the you can take a look at the CDA fed average paper where it's mentioned about the beta distribution. The noise it uses a lambda noise filter based on a beta distribution. The noise filter increases when based on a beta distribution. It's an algorithm basically. So here actually the noise filter increases when the age increases, but uncertainty is high, as we see in the example here. So to perform drift detection on CDA fed average, one has to apply unconstrained optimization on the lambda, because lambda keeps on changing based on the age. So it is varying. So we have to find an optimized lambda for that group. Just a threshold would not work well, because if you optimize the lambda for because the algorithm is dependent on the noise filter, we have to optimize the lambda, we get good results, and that too it should be measured against drift synthesize scores. So we should have a classifier which actually measures the drift in a drift synthesize classifier, and then train this model onto the drift synthesize one. Apply noise filter, try and predict the patterns of the noise filter, and then infer from it, and then implement that CDA fed average method. Such a denoised image will have a corresponding residual image which, when compared against for correlation p-value with student t is obtained. For large samples of data, G-test is obtained. So this is a concept drift where I considered parameters such as age or time, then methods, image denoising, image noising, image reconstruct, image perturbation, explained by rollover mean or standard error, PSNR over age, phase classification by age. So this is GANs over statistical phase model include additional age variable. Reconstruction by statistical phase model is chosen due to the elimination of aging parameters within an image according to paper. Age is already present in the dataset and statistical analysis explains it. There are overlaps of machine learning classifier parameters when drift by age is taken into consideration and the error is huge. The noise filter is a data concern instead of the algorithm, hence it forms a part of a model. Perturbation produces an effect that corresponds to misclassification, which is essential for drift measurement of an algorithm. So looking at predictions of phase classification and accuracy or error differences between regular and age drifting, there is no huge change. Then measuring CDA fed average method for optimal environments requires a ground truth, which we actually showed there. Then I formed the new decision model which is using real virtual as well as existing or synthetic dataset. So existing dataset is assumed to be more drift severe because of its natural surroundings. Synthetic dataset has more knowledge loss due to lack of addressing the complexity as par with the existing dataset. Then problems encountered. So the training using the baseline transformers model which can scale for large datasets encountered a problem which will be solved by using appropriate methods of evaluation. Evaluation technique for a pre-trained model for face recognition present in the repository is incomplete actually. So the dataset size used for the transformers model was only 6,000 images. This is another problem including the test set. So I should use a larger sample dataset. Then the statistical analysis using confidence intervals for small sample size showed larger uncertainty, but power-based analysis provided a considerable insight into detection for change. Another set of problems are power-based analysis was better explained by PSNR analysis over age, which revealed an average drift in quality of images. But PSNR-based analysis answers research questions in 2 dimensions, whereas power-based analysis considers Euclidean distances. Explaining through virtual drift rather than real drift is more concrete. Synthesizing images through GAN models is time consuming and takes a lot of time for evaluating drift. Then drift synthesis must persist the images onto disk and then evaluate them using an algorithm. Then plans for resolution. The transformers model will be trained with large datasets and with better methods of evaluation. The face recognition model will be presented with a detailed and better methods of evaluation than existing one. More machine learning based explainers based on age drifting will be provided for better explanation. So for this one I actually conducted an interview with a PhD student based in Kingston University, and he explained me that the training with larger datasets is more preferable with transformers model because the models are new generation models and the dataset size must be huge in order to improve the accuracy rate for that model. This interview will be posted in my report as well. Then the methods for future work. The new algorithm based on the statistical phase model is to be created. The new algorithm must run on JAX such that parallelization can be performed and optimization can be run on CDA fed average. The new algorithm must depend on a model rather than a pure algorithm. The new model based algorithm must be tested on new datasets such as house pricing. Then drift adaptation will be integrated with existing implementation of drift synthesis using GANs. Then future plan. Federated learning shall include only training and setup of FATE on Intel Dev Cloud. Alternatively, JAX or Flower may be introduced as a backup plan for federated learning training due to the complexity of FATE servers or configurations, but FATE standalones are a good option. Feedback on the synthesized images will be collected over meetings as well. Ethical, legal and professional issues. So paraphrasing quotes and including references will support more legal and professional issues related to the project. Deductive disclosure of dataset information will improve the ethics considerations. New dataset analysis should satisfy the ethical considerations mentioned in project proposal. Collection of data from internet, deductive disclosure and focus groups with materials of implied consent. Open source licenses such as GPL or Apache are different from each other. Participating in Intel Dev Mesh projects and submitted. I also participated in Intel Dev projects and submitted the concept work. So here is the concept project. Any additional review on new datasets such as synthesizing data must be accompanied by collection of ideas and concepts using web form. So here is a web form to submit that. So thanks to my professors who has helped me complete this to until the stage, and it's been very helpful working with my professor, and Kingston University is very helpful as well. So this is my formative viva submitting, and I'm Ashwin Vijay Kumar. Thank you.